not at my email. So again, we're still recovering from the days off. Our motion test is Monday. Again, the pluses and minuses of a Monday test, right? You've got to remember that you have a Monday test. But you also have all weekend to study for it, so that's I'm trying to make it sound like a positive, but whatever, it is what it is. It's going to have to be Monday, unless you want it Friday of this week, which that sounds like a terrible plan, to do 2 days of notes and then take a test. It is on the easier side of the test that we take. So if you think you didn't do great on the test we just took, which is usually one of the harder ones because of all the different integration things, this one's a little more straightforward. It's like there's only one topic. You get a calculator for part of it. We've kind of done some of it before. So, Mallory, you okay over there? So let's walk through the notes. Again, I hope most of it looks familiar. In fact, let's just start. Let me give the super summary of the notes up here at the top. How do we get from position to velocity? What do we do? Take a derivative. And how do we get from velocity to acceleration? Take another derivative. Okay, that we've done before. If I give you, in fact, there was one question like that on the test. It was supposed to be an easy one. Hope you got it. Where it gave you the position and said, when is the thing at rest? So hopefully you took a derivative of position and then set it equal to 0. That was Ashlyn, is that a sigh of relief that you got that one right? I mean, that was an old one, a review one, supposed to be an easy one. And refresh your brain that to get from position to velocity, you take a derivative. To get from velocity to acceleration, you take a derivative. How about going the other way? How do you get from acceleration to velocity? And you take an antiderivative. And to get from velocity to position, an antiderivative. So we've done the sort of the left-hand side of this before. We had a unit on that, using derivatives to get from position to velocity to acceleration. We're going to still need that, but on this unit we're going to add going backwards. Given acceleration, back up to velocity, back up to position. Now, what makes that harder is, I guess, two things. First is antiderivatives are usually harder than derivatives, right, as that last test might suggest. But also when you take an antiderivative, a lot of times plus c shows up. And so we'll have to deal with the plus c and figure out what the c is. Now, we've done that before, we just haven't done it with motion. So this is why this is on the easier side. I'm not going to say it's easy because it's still calculus. We're still taking derivatives and antiderivatives. But we've done derivatives before. We've now done antiderivatives. And we've done motion in general before. So now we're just going to kind of put the pieces together. And if you know the pieces well enough, this one isn't bad. I think most of the struggles still come in if you hit one that you don't know a derivative or an antiderivative. Okay, so let's walk through this. Again, most of this we already know, but we'll walk through it again. Position function. Typically we use s or x or y. Usually y is if we're going an up and down motion, x is a left and right motion, but any of those could be used for position. Position on a horizontal, that would be the x, or vertical line. Units could be inches, centimeters, meters, feet, etc. This is the location of the particle or the object. If you are the object, then this is your location. This is where you are. The position tells you where you are at any given time. Velocity function, called v of t. Velocity is the instantaneous rate of change of the position of the object. Right? That's a fancy way to say it's the derivative of the position. So v is s prime or v is ds dt. Again, we said that already. To get from position to velocity, take a derivative. And we've done that already. We tested over that last semester. Units would be, like you know velocity units, anything distance over time. Any distance over time units. So feet per minute, meters per second, miles per hour, any combination of distance and time you like. We've done this before, but be careful. Velocity is related to speed, but they're not identical. Speed is the absolute value of velocity. Speed can only be positive. Right, we've done that before. It's just reminders. These are all reminders right now. If you're driving a car forward, your velocity is positive and your speed is positive. If you're driving in reverse, your velocity is negative, but your speed is still positive. Right? So if you're driving backwards at 3 miles per hour, you would say your speed is 3 miles per hour. That's how fast you're going. But velocity has a direction associated with it, so negative 3 miles per hour. And I'm guessing most of you had physics, so this is also kind of the overlap with physics. If velocity is positive, the object is moving to the right or up. Right? That makes sense. This fits with how the xy plane works. Right is positive, up is positive. If velocity is negative, then it means you're moving either left or down, kind of depending on the situation. If the velocity is 0, the particle is not moving, is said to be at rest. Again, we tested that on that test yesterday. All of this is still old news. Acceleration, called a of t. It's the rate the velocity is changing. So dv dt. This means, some of you said this earlier, that's the second derivative of position. So units would be anything, any distance. You know what? Let's do it this way. It would be any velocity over time. That would be your units. Now, that usually simplifies to distance over time squared. But, and maybe you've heard this in physics, some physics teachers will say meters per second for acceleration. It's the same thing as meters per second squared, but meters per second is kind of preserving that change in velocity over change in time. So it may seem weird to say it that way, but when we say meters per second, it's helping to emphasize that that's the change in velocity over a change in time. So either one of these are acceptable. Obviously, meters per second squared is easier, but meters per second kind of preserves the concept of what's going on. If acceleration is positive, velocity is increasing, although we have to be careful, this does not mean the speed is increasing. Do you know when would that be? Like, how could velocity be increasing, but speed not increasing? It has to do with positives and negatives. If V1 is negative 8 and V2 is negative 5, that velocity is increasing. That seems weird to say, but think about a number line. You're increasing on the number line. Your speed decreased from 8 to 5, but your velocity increased. So we have to be super careful with velocity and speed. Speed increasing, speed decreasing. Speed is the absolute value of velocity. So speed is increasing. We don't ever use this. The derivative of the absolute value is positive. That's true, but that doesn't help us. Unless, I guess, we had a calculator. We could do that. But without a calculator, it's cumbersome, difficult to take the derivative of absolute values. So we've done this before as well. So here's your another reminder. Speed is increasing when A and V have the same sign. Speed is decreasing when they have different signs. So if A and V have the same sign, I think of it as like they're helping each other out. They're going faster. They're pointing in the same direction. They're either going faster forward or faster backwards. If they have different signs, then they're like fighting each other, so you're slowing down. Okay. Everything on that page is old news. Again, I know that doesn't mean you know it perfectly, but hopefully it looks familiar. Right. Displacement. We're about to start to get into some new information here. Displacement is the change in position from time A to time B, as opposed to total distance. Let's do the classic example here. The displacement of one time around the track. So, do you remember what your displacement is if you run around the track exactly one time? Zero, because you haven't gone anywhere. As opposed to, we'll go a little out of order here, total distance traveled one time around the track. Fourth of a mile, 400 meters. But the main thing is displacement versus total distance. Displacement is just where you were, or where you are minus where you were. Okay, now we get to the new stuff. Now that we know integration, change in position can also be written as the integral of, I'm going to write this one other way. So we know displacement is SB minus SA, right? Where you are minus where you were. But that's the same thing as the antiderivative of the derivative. But the derivative of S is V. So here's one of our new formulas. I'm not sure how new it is, but it uses old variables, old techniques, but a new application. So displacement is the antiderivative of velocity. Total distance, you might remember this on that test. It's kind of a pain to do total distance because you have to add up all the changes in position. Right? So you have to add up this plus this because the thing was going back and forth. Does that sound familiar? We had to draw out the motion diagram, and you had to add up, well, this distance plus this distance, which was tricky because you changed direction, plus that distance to get the total distance. So it's kind of a pain. It's going to be a little easier with a calculator. Let's back up here. To find the total distance traveled by an object, you have to add up all the changes in position when the object moves to the right, and all the changes in position when the object moves to the left. So that's why we would draw out one of those motion diagrams to figure out when are we moving right, when are we moving left, and add up all the pieces. So if the particle changes directions, then you end up with, and I remember some of you would safe stop this thing and you would put stuff like this as your answer, which was fine. Although you have to be careful. This would not be okay. You'd have to plug in the pieces there. But a lot of you plugged in pieces, left absolute value bars, and left it alone, and that's okay. Clearly, this is cumbersome. We must determine the times that the particle changes direction, right? You remember doing that? Oh yeah, this was t equals 1. And then maybe it changed over here at t equals 3. And so we had to get the distance from 1 to 3, but also the distance from 0 to 3, or 0 to 1, and 3 to 5, or whatever. Just, it was a pain. Because you had to find positions at each time, and then use that absolute value thing, make sure everything's positive, to find the total distance traveled. Blah, 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 blah. If we have a calculator, it's much easier. Okay, we didn't do a Riemann sum project, but total distance traveled is the integral from A to B of the absolute value of velocity. In fact, let's put the displacement formula right here with it, because that helps us see the difference. So displacement goes with velocity. Those kind of go together. Distance is related to speed, which is why you take the absolute value of velocity. Again, you would only do this with a calculator because we don't do antiderivatives of absolute values unless they're like super easy and we can do them graphically with a picture, an area. So this is almost always with a calculator. Okay, summary of motion. Position, velocity. Here's one that we like to mess up. Average velocity. Average velocity. You don't add up velocities and divide by time. Average velocity is S2 minus S1 over time. So you don't need a derivative for average velocity. That's what gets people. They see velocity and they think derivative, but average velocity, you could almost think algebra velocity, and then just use the good old slope formula, or velocity when you first learned it in middle school. Change in distance over change in time. Moving right is positive, moving left is negative. You know what acceleration is. Average acceleration, here's another one that'll get people. Like average rate of change is the algebra rate of change. The average velocity is the algebra velocity. And the average acceleration is the algebra acceleration. So when you see average on there, that's your hint to we're not really doing calculus, we're doing algebra. And so it's an easier process, but I guess just because we're so used to doing calculus, when you see velocity, you start taking derivatives, accelerations, derivatives. But be careful. The average is what's going to mess people up. Speed is absolute value of velocity. We knew that. Speed is increasing when they have the same sign. Speed's decreasing when they have different signs. And then displacement versus total distance. Right? They're like similar concepts, but they're not the same. And that's reflected in their equations. They're similar, but total distance uses speed, whereas displacement uses velocity. Let's do some example problems there. With calculator. So, if you need to borrow one of mine, you can borrow one of mine. Don't do trace, okay? Trace is going to mess you up because you're going to get right there, but that's not the right answer. So what do we do to get it's not the exact answer, to get a better answer? Second calc, we're looking for a 0. And then if you make it that far, then we should write some of this stuff down. So this goes in for y1. Then we're going to do second calc 0. And if you make it that far, the calculator will walk you through what to do the rest of the way. Left bound, question mark? So that means get to the left of the 0. And press enter. Right bound, question mark? Get to the right of the 0 and press enter. Guess you could just press enter again. And so there's my time when acceleration is 0. So A equals 0. And t equals 1.318. look, answer choice C is 1.32. Is that what we're looking for? That's the time. But the question was, what is the velocity? So I know why answer choice C is there. It's not right, but that's the time that we'd be looking for. So how do I find the velocity if I know the time? Just plug it in. So 4 sine 1.318. I'm a little worried about how accurate 1.318 is, but my answer choices are all far enough apart, and I've carried 3 decimals, so I'm probably going to be fine. Minus 1.318. So if there were multiple answers that were really close, maybe I need to carry more decimals, but there's only one of them that's close to 2.55, so I feel pretty good about that answer. Using our calculator to find it. Let's see. Let's do this one more, and then I think we'll be probably done for today. Calculator. Look at all this. Little side note while I'm looking at this free response question. For this motion test, I think I mentioned this to somebody yesterday. It's going to be part with calculator, part without calculator. The in-class part will be multiple choice, which suggests that there's an out-of-class part that'll be a free response question. And rather than trust your honesty, I will say that the out-of-class free response part you can work together on. So, yes, you'll have a take-home, work-together part of the test, right? It'll be like 20% of the test. So you should get that 20 points definite, right? Like, I mean, I'll check and make sure all your work's there. I won't know if you just straight copied somebody. I hope you'll take it to learn it, not just copy it. What's that?
Like a picture we're sending in, or?
No, I will hand you the paper and say, this is due on, I don't know, I hadn't even decided yet. Probably Thursday, because I don't want it to go over the break. Maybe Friday, whatever.
We get 3 days. There's 3 days.
Yeah. So, all that to say, so you were worried about time on that day. So it'll be, I think, 20 multiple choice questions on the day. Maybe a few more, a few less. Still working on the test. And then the free response portion will be take home, work together, bring it back. So that should be nice. Okay, back to this problem. Speaking of free response questions. And it'll look something like this. It'll be long, but you'll have together and multiple times, so you should be fine. The velocity of the particle moving along the x-axis is given by, okay, I'm glad this is calculator because that doesn't look good. The position of the particle at time 0, x of 0 equals 2. What is the acceleration of the particle at time 3? Well, how do I get acceleration? Derivative of velocity at time 3. I don't know. Have we done this before? Have we put let the calculator do our derivative for us? Okay, so x minus 7 cosine of x. I'm going to change my window to go -1 to 8. Again, I like to look just a little past to make sure I'm seeing everything. I don't know if -5 to 5 is a good choice or not. We'll see. Yeah, close enough. If I need something further down, I'll look at that later. So how do I find, so this is velocity. I might even want to say y1 equals velocity. So how do I get my calculator to tell me the derivative of that thing at 3? Do you remember? The good news is it's the same place the 0 was. Second calc. And I want dy dx. And then it doesn't have a question mark there, but it's asking you where it wants dy dx. And you can use the arrows, but it's unlikely that it's going to land on exactly 3. Right? Like I can get to 3.02, so it'd be close, but I don't want close. This is sort of hidden, but all you got to do is push the button 3, and it says, oh, x equals 3. That's what you want. So there's my derivative at x equals 3. So negative 0.2, always 3 decimals, 0.426. And no units were given in this, so I don't have to worry about units. Okay, so are you good with that? Like this is part of this is like remember how to use the calculator. Second calc, and then there's all your options. Dy dx is what we want for that one at 3. So, I mean, it tells you dy dx, but we know that slope of that graph is acceleration. The calculator doesn't know we're doing a velocity acceleration problem, but it does know that how to do a derivative. All right, part B. What is the position of the particle? Okay. So that's a great question. Units, sometimes they attach a point value to the unit, but if they do that, they will tell you to give the units. This one, it didn't even give us units for velocity, so there's no way they could ask units on anything else. All right, I've got velocity. How do I get position? Antiderivative. So I want to antiderivative the velocity. That will give me position, but if I leave it blank, I'm going to have a plus c. I don't really want to do that. I'd rather have some limits on there so that my calculator could do this for me. So I'm hearing 0 to 7 because that would give me x of 7 minus x of 0. Okay, I'm looking for x of 7. Like that's the point of this problem. So I'll move x of 0 to the other side, and I'm going to let the calculator do the hard work here. So let's see. Do you remember how to find the antiderivative in the calculator? Math. Then, let's see, I think it's 9. Math 8 is a derivative, Math 9 is an integral. If your calculator doesn't look like that, I think they're all updated now, but the old operating system didn't look like that, and you have to know where to put commas and stuff. So, Math 9. And again, when it pops up like that, it's pretty easy, because then you just know where to put the things. 0 to 7. I think we did this. So do you remember I don't have to retype all of that t minus 7 cosine t because that's in for y1. So I can put y1 in there. So vars, y vars, y1. So we like using the y equals screen because then you can do the graph and you can use the y variables. And that's not exactly my answer. What have I messed up on this or not finished yet? I need to add where it started. That's its change. That's start plus displacement. So we just found displacement, but I need to add 2 to that. Plus 2. Ben?
I got negative 24.5 in my calculator.
Are you in radians? That would be the main thing to check.
Yes.
You are in radians?
Yeah. This was degree.
No, you want to be in radians. Go back and make sure y1 is correct. X minus 7 cosine of x. And then you could redo math 0 to 7 y1 dx. That is the major question, Mallory, that you just asked. That is, you know to take an antiderivative. That's not the problem. It's just you got to remember to put those correct starting points in there so that you can figure out your position. Otherwise, you'd end up with a plus c, and you'd be doing it by hand, and so use those limits, pick them correctly. Ben, did you get it figured out over there? Holly got it figured out for you. Part C. On what interval is the particle moving to the left? So what would we be looking for if we're moving to the left? What's negative, though? Velocity is negative. In fact, there's our justify your answer. So velocity is negative. How can I know where the velocity is negative? Well, I already have a velocity. In fact, I have a picture of velocity. So where it's less than 0, so that would be, I wish I could highlight my calculator here. Less than 0, right there, and right there. So let's use the calculator to figure out where those, their spots are. So 0 to something, and then something to something else. But I got to find those somethings. How do I find the somethings? What am I looking for? The zeros. So second calc again. And again with the left bound, right bound stuff. Left bound, right bound guess. .571 is my first zero. So my graph is below the axis, means my velocity is negative, means I'm moving to the left from 0 to 1.571. And then I need to go find the other ones. Left bound, right bound, guess. 4.712. And then the last one, left bound, right bound, guess. I do need to be careful because this experiment only goes to 7, so that makes sense that's why it goes to 7. I'm going to stop there. And that's my justify. Justify your answer is, well, where is the velocity negative? Right there. So I don't need a paragraph of justify, I just need to explain what I was looking for. Part D, what is the displacement of the particle from 0 to 7? Okay, how do we get displacement? I could do S7 minus S0, but then that would be a lot of work. Actually, that would not be a lot of work, because we already have that. We have S7 and S0. We also already did the integral from 0 to 7 of v of t dt. So I can scroll back in my calculator, and that was negative 0.246. Again, at this point, there's two ways to get that. We know S7, we know S0, and we know this, so that's all the same stuff. All right, part E, total distance traveled. How do we do that? How do we find the total distance traveled? How is it different than displacement? The absolute value. So the absolute value of v of t from 0 to 7. Again, I don't want to do that by hand. I don't think I could do that by hand. But the calculator can do that. So I'm going to do that same math 9, but this time I'm going to put my velocity in absolute value bars. So math 9, 0 to 7, and then I need to figure out where absolute value bars are. Pretty sure they're under math, num, abs. Math. No, I mean you pick abs. And again, on the newer operating systems, it has the bars there, so you know you're doing absolute value. V of t, I already have that in for my y variable y1. And so that would be a really complicated thing we're asking the calculator to do, but that's fine. The calculator can think for a minute. We really had to think for that one. 15.67 or 15.680. What do you think about the relationship between total distance and displacement? One of them will always be greater than or equal to the other. Which one is always going to be bigger? The total distance. They could be the same, right? If you went the same direction, they'd be the same. But displacement will never be bigger than distance. All right, part F, speeding up or slowing down. So what do I need for speeding up and slowing down? I've done this problem before. I need acceleration and velocity. So I need A of 5 and V of 5. Okay. Having just one of those is not enough. Some of you on that test, you'd say, oh, acceleration is positive, so we're speeding up. No, speeding up, slowing down, you have to get both of those. So let's see, V of 5, that's easy. I'm going to... there's a bunch of different ways to get V of 5. Especially since all you need is, whether it's positive or negative, you can just look on the graph and see that V of 5 is negative. That would be the easiest way to do it. Now, maybe a fancier way would be second calc value at 5 and find out exactly what it is, but we don't really need to know exactly what it is. It's negative, and that's good enough. How about the acceleration at 5? Derivative at 5. So second calc. Although you might be able to tell by looking. If 5 is right there, what's the slope of that graph? Positive or negative? Negative. And so again, you could use your graph and just say it's negative. And you can also find the value, negative 1.63. So what does that mean? What is the conclusion? We're speeding up. They're pointing the same direction. So we're speeding up. Speeding up in the backward direction, but speeding up. Alright, at what time is the particle farthest to the left? So what happens when we change from moving left to moving right? Moving left to moving right. What's changing when we make that heading?
Like, just 5 and 16, because they're both the same time, we can even work it out.
I suppose we probably should. Same sign for A and B. So what's changing when we change direction? Here's your options, S, V, or A. If you change direction, which one of those is changing? The sign is changing of one of those. V. The sign change. In fact, which sign change is it? If we're moving from, let's see, we were moving left and now we're moving right. So we need to see where our sign changes from left to right, or from negative to positive. So there's my picture of velocity. Its sign changes from negative to positive. Right there. Zero. I think we already know the value of that zero, but go find it. Left bound, right bound, yes. So time equals 1.571. Yeah, we had already found that, but justify your answer. I would say it moves left until 1.571 and moves right after 1.571. Last one, perfectly timed. Average acceleration? How do we find average acceleration? V2 minus V1. Yes, algebra. So that's just V7 minus V0 over 7. Whatever you get for that. I don't know. How about that?